I'll record to this. Okay, so we are started here. So let me take us to that PowerPoint that, again, like I said, you guys can actually download and go over a few things. I'm going to be very honest with you guys right now. I just had interviews all afternoon. I've been watching Zoom screens for all afternoon and or 8 hours yesterday. I'm a little fried. So I may have to take a couple of breaks as we go along, okay? So hopefully you don't mind. And again, if you have questions, just uh, I'll make some pauses for you to ask me questions. If not, if you can't wait, just put them in the chat, and hopefully I'll see it and be able to call it up, okay? You can tell my voice is a little shot here also, so please bear with me. All right, so here we go. Let's go ahead and look at that PowerPoint. Hold on, let me set it up for us. Hold on a second before we do that. Let me set it up so that it will be working when I share it. Here we go. Ba ba bam, ba ba ding, ba ba doom. Here we go. So this is our practice, our review session. So here is what I'm going to do. I am going to go over an outline of what I think are the major, I would say, content topics and skills that you need to kind of work on, things you need to practice. Now, I'm going to let you go back later on, and on your own, you're going to have to go back to the problem sets at the end of each chapter and perhaps try out the ones that you didn't try out for homework to see how you do, okay? Besides the one that are on this PowerPoint here that I'm sharing with you and that you can download on your own canvas, okay? There is no shortcut. This is a set of units that requires like a lot of practice and a lot of mastering. It has to do with, you know, how quickly you can access in your brain. Okay, what is the approach here? What is the approach here? What table do I need here? What information do I need to get for this? Okay, don't forget, in any problem that you get in an exam, you're not going to be asked to remember or memorize anything other than the KW. Everything else will either be on your handout or it will provide it to you. So if you need the Ka of an acid or the Kb of a base or the Ksp, things like that, that's what we provided as part of the question. You don't have to memorize any of that stuff. Okay, so here we go. Let's go ahead here and let's see what we have. So this is essentially, hold on a second, let me so far out of my way so I can see it. So the first unit that we cover for this exam is equilibrium. And this is the foundation for everything else, you know, the other two units that we covered. First of all, make sure that you understand what equilibrium means and what it isn't. I think in the lecture video, I go over what equilibrium is not, right? And what it is. How do you determine based on the formulas, on the equation, what the formula is for the equilibrium constant? And if you are given a value of it, what does that tell you about the position of the equilibrium? We said, does it favor reactants? Does it favor products, right? Remember, we did that kind of like analogy there. Also, how do you determine whether a system is at equilibrium or not? Well, you will be given certain information about the concentrations or the pressures of the reactants and products, and you'll have to determine the reaction quotient, QC, and then compare it to what the equilibrium constant is and determine, okay, is the system is at equilibrium or not? If it isn't, which direction is it going to go in order to achieve equilibrium? All of that is covered in the lecture videos and in your book. Like I said, we have a way of sometimes expressing equilibrium in terms of partial pressures of gases, and we have what's called a Kp. And the relationship with the Kc and Kp is not, they're not equal, they're not the same necessarily. So in your handout is the formula where you can convert between one and the other. Very important, in this unit, we teach you how to do ICE tables, right? So you need a lot of practice with that. There's kind of like no, unless I'm sitting with you and solving a problem and I can see how you approach it, I don't have a one-size-fits-all strategy for how to set up ICE tables. Just make sure that in your mind you understand uh, in the information they give you, are they giving you initial conditions? Are they giving you final or equilibrium conditions? What kind of information are they giving you? Are they giving you the equilibrium constant, or are they asking you to calculate the equilibrium constant based on what they give you? So it's very important that you practice several kinds of exercises, like everything else that we do here that involves math. There's always, I don't know, three, maybe four variables, and essentially the problem gives you three of them, and then you have to figure out, okay, what's the one that I have to find out? Or sometimes they'll give you two, which leads to finding easily what's the missing one, and then what's the unknown. So every math problem is kind of like that. So for example, in an ICE table, you might be given the initial concentrations, you might be given the final concentration of one of the components, and then asked to calculate what's the equilibrium constant. So obviously you had to build your ICE table in that, understanding that in between what they give you and finding the equilibrium constant, you're gonna have to set up an ICE table with some excess or whatever letter you use and figure out, okay, what are the concentrations at equilibrium of all the components, okay? The other thing that I want you to review is the Le Chatelier principle. This plays a major role in all of our discussions about equilibrium, whether it's gases, whether it's acids, bases, whether it's solubility, and later on we're going to go into thermodynamics and electrochemistry, and again this whole idea of Le Chatelier is going to come back. So make sure you understand the idea. I think in my videos I do the analogy of the seesaw, little teeter-totter kind of thing. So I don't know if that works for you. You may have an even better analogy than that. And if that's the case, hey, be blessed and go on with that one. Work with whatever fits, your brain circuits, the way you process information. For me, the analogy of the seesaw works because it's very visual and it's very easy to convey. And if you guys want, you play some music in the background, you make it into a dance. Do the seesaw, you know what I'm saying? Anyway, so let me go ahead and do this. I'm gonna stop my share here for a moment. I want to give us some practice exercises here, and they are in the PowerPoint. Now to do this, I'm gonna have to switch over to this camera here. Let me see if I can do this, okay? I'm gonna try to place the pin here. Let me see if I can switch over here. I'm not being able to. Oops. Well, so let me ask you if you're seeing like a hardwood kind of table or something. Does it look like, is that what you're seeing? Give me a thumbs up on the reactions there if you're seeing that. Or maybe you're seeing my head still. Does that work? Or throw me a message in the chat saying, yes, we can see it. And I'm gonna put in this in there. Can you see that now? It's a paper with equilibrium. Okay, I'm seeing a thumbs up. Okay, somebody says they're just seeing my head. Okay, I need you to navigate to this screen. I pinned it right now. Let me see if I put myself on the speaker. Okay, so somebody says it's on the camera screen. Okay. All right. See. Okay, so everybody's got it. Okay, so it's seeing. So this is a question that I have on the thing, but for some reason, hold on a second. Let me do something here. I'm gonna take out my video from here. Hold on a second. I need to do something here. For some reason. Well, the problem that I have right now is that I'm not able to. I'm not getting this screen that you're seeing. I'm not getting it on my camera itself. I can't get it to come off. Let me see. Okay. Okay, here we go. So I'm gonna try to zoom in a little bit on this. There you go. So hopefully everybody can see that question there. Yes, now it disappeared on your screen. Oh, here we go. Sorry. I'm seeing something totally different on my screen. But so here's a question. The following reactions occur at 500K. Arrange them in order of increasing tendency to proceed to completion. In other words, from least completion to greatest completion. Now, let me tell you one thing that happens here is these letters, right? So K. So the letter K, uppercase, can mean Kelvin or it can mean the equilibrium constant. I try to make an effort so that every time that I mean the equilibrium constant, I'll put a subscript. So I'll either put KP or KC or KX or KA or KSP, you know what I'm saying? So that it doesn't get confused with the K of Kelvin. So the 500K means 500 Kelvin. That's not an equilibrium constant. Understood? I think I saw this kind of problem, I think, in a quiz earlier this semester or something like that. Okay, so here are 4 equations, 4 values of K, and hopefully you can see those values. And the question is, which of these has the least tendency to go to completion? In other words, to be favoring the right side, the product side, and which one to have the greatest tendency. So what's the strategy here? Anybody want to mute their microphone and tell me what the strategy is? What am I looking for? The largest value of KP is going to give me what? Anybody? Or put it in the chat. Sorry, having a problem. See, my touchscreen even doesn't work right now. There you go. Most completion. Very good. Thank you, Gabe. Most completion. Right? So that means that the smallest value will give you the least completion. So which of these guys has the smallest value? I have 1.7 times 10 to the negative 2, 1.5 times 10 to the 3, 1.3 times 10 to the minus 5, 5.9 times 10 to the minus 5. So which of those is the smallest value that you have? That's right, this guy here. So that's the guy, number 3, that has the smallest value. Who comes after that? Number 4, right? And then this guy here, 10 to the minus 3, and obviously the guy that is, greater than, this guy is like greater than 1. So that means that that guy is going to be the biggest one. That's the one that's going to be completed. So make sure that we understand how to approach this kind of thing. Remember, a large value of K means that you can go, as high as you can. Somebody asked me to go to full screen. Let me see full screen. Oh, there we go. That works better, right? All right, here we go. So again, any questions about this type of question, type of problem? You understand that? I know what you're gonna say. I get confused with those negative exponents. Okay, what I gotta say is just practice. I don't have a I don't have a way of getting inside your head and telling you a one size fits all idea of how to tell if something's bigger or smaller. Just you got to go back and review how do you make sense of values that have negative exponents and which one's bigger. Remember, the more negative the exponent of 10, the smaller the value. But within that range, like in this case of 1.3 and 5.9, of course, the coefficient tells you which one is bigger as long as they're in the same kind of range there of exponents. All right, cool. Sorry, guys. Like I said, I'm out of practice. Okay, here's another kind of problem that you might encounter in these types of questions. All right, so let's say that, oh, let me go back to a full screen. Let's say that 2 moles of PCl5 are placed in a 5.0 liter container. Dissociation takes place according to the equation, and it gives you there. At equilibrium, 0.40 moles of chlorine are present. Calculate the equilibrium constant for this reaction under the conditions of this experiment. Okay, so when you hear a problem like that, what comes to mind right away? You're gonna have to build. Say it together. Ice. That's right. You're gonna have to set up an ice table. So let me put it up here on the top. So you're gonna have, oops, sorry. You have your PCl5 guy, right? Then you have your PCl3. I'm not gonna write the symbols here because right now I'm just working. So I don't have to actually, I just know that they're all gases, right? So again, you know, ICE. Now be careful how you do this, because even though these are gases, we are being told amounts in terms of moles. So essentially, they are asking for Kc, not for Kp. Be careful. Secondly, it's in a 5.0 liter container. Normally, we do these things in units of molarity, right? So that means that we had to convert these things to molarities. Now, if all of the species are in the same container, that means that the volume is going to be the same across the board. But you have to be careful because of exponents or multipliers. So I honestly would recommend, right? I would recommend that you essentially go ahead and convert everything to molarity. So this guy, it says that you have 2 moles in a 5.0 liter container. Of course, you start with nothing here. And now you have to calculate, well, what is the change? Well, 1 mole per liter of this guy is going to change into X liters, X moles per liter of that, X moles per liter of that. So at the end, you're going to have here 2 divided by 5 minus X. This is going to be X, and this is going to be X. And of course, you can calculate this, right? You know that this is going to be what? 2/5 is what? 0.4, right? Any questions so far? Cool. Okay, so our Kc expression is PCl3 times Cl2 divided by PCl5, right? And we had that the top part is X squared and the bottom part is 0.40 minus X. But look what it tells us. At equilibrium, there are 0.40 moles of chlorine. So that means that X, right, this guy, is 0.40 moles in 5.0 liters. Now, remember, if you remember Professor Rollback's video, what she did was she would add a fourth line here, another E, which gave you the actual values. It would have given you what X was. You could actually solve for all of these. And that's fine. If you want to do that, that's fine. I typically just do it as a separate calculation. Again, that's just the way my brain processes things, but you don't have to. So going forward, essentially, you have to find out what this is. You know, so you're gonna, oops, sorry. It's over here. You're gonna calculate what this is, and then you're gonna substitute, and then you're gonna do your final calculation. I don't have the values here. You can fit in what you want. I just wanted to make sure that you recognize when you see a problem like this, the automatic go-to is ICE table. And then once you build your ICE table, find out, okay, what other information they gave me. So they gave me the initial and they gave me the final of chlorine. And because I built the ICE table, I can pretty much put everything in there corresponding. Okay, all set? So I'll let you guys work on the math of that. And then you can check the downloaded PowerPoint and you can see what that is. Okay, cool. All right. Here's another question. This one is about, let's see. Ooh, Le Chatelier. Yeah. Here's a Le Chatelier question. If I can fit it in here. Here is this is like a typical, I do this a lot. I make up formulas, I make up compounds. I use symbols that are not on the periodic table. I'll do that sometimes just so not to get you guys distracted. I try to do that in the quiz where I gave you, what is it, aniline or pyridine or something. And I told you, don't worry about the formula, just put something in there. Some of you guys actually looked it up. Okay, more work for you. You didn't have to. But anyway, I make up a lot of formulas sometimes. So here we go. Le Chatelier, which says that if there's a stress placed on a system at equilibrium, the system is going to compensate to reestablish equilibrium. Again, do the seesaw. So let's see here. What is the effect of adding more B? Which side is B on? Product, right? Feel free to unmute yourself and yell out the answer. Don't make me open the chat to read it. And feel free to uncontain yourselves. So B is what? Product or reactant? Product, right? So that means that I'm making the product side heavier. Le Chatelier. Let's see how are you guys looking at me? Okay, like product side is heavier. Wait, how are you guys looking at me? I think I'm inverted. Let's see, I don't know. Let me just point at it. Product side heavier, which means you have to compensate, right? The seesaw is going this way. So I want to bring it back to equilibrium, right? So that means that you're gonna have to shift which way? To the reactants. Very good. Okay, let's try number 2 here. Oh, here's an interesting one. So it says this was at 450 Kelvin. Again, make sure, see what I'm saying about the K? Okay, so that K, 450K is for Kelvin. The other K has a subscript, so that's the equilibrium constant K. So don't get them mixed up. So here we know that at a temperature of 600 Kelvin, Kx is 1.8 times 10 to the minus 5. Can you guys see that? Let me see if I can zoom in just a little more. Oops. I can see that. Okay, so what is the point here? The point here is that if I increase temperature, what happens to the equilibrium constant? Did it increase or decrease, right? okay, decreased. And remember we said that the equilibrium constant is sensitive to temperature, right? In other words, if you change the temperature, you change the equilibrium constant. Now, the question is, what kind of information do we get from knowing that when you increase temperature, the K equilibrium decreased? So the question is going to be, was this a endothermic or exothermic? That is, exothermic. Remember, if it's endothermic, that means that reactants receive heat in order to go to products. If it's exothermic, it means that reactants release heat when they go to product. Oops, sorry. Bring this back up. Oh, oops, not that much. Oh, almost had it. So again, remember what you say is, well, if I increase the temperature, if it's endothermic, that means I'm pumping heat in here. So if delta T is positive, then what should happen is, this is Le Chatelier, you're increasing the thermal energy on this side, which means you're going to shift to products. And therefore, the equilibrium constant will increase, right? Because remember that equilibrium constant is products over reactants. If this guy is exothermic and I increase the temperature, I'm increasing the product side, right? So that means that I am going to increase this, which means my system will have to shift to reactants, right? And remember, if you shift to reactants, that means the bottom of that ratio of the equilibrium constant is bigger. So that means that the equilibrium constant will decrease. Okay, so what is the scenario we're seeing in this case here? When we increase the temperature, the equilibrium constant decrease. So which of these two does that match? Exothermic, very good. Oops, sorry. Let's hit a little thing in here. Very good. So that means that this reaction is exothermic as written. Always remember that when we say, you know, this reaction or whatever, this equilibrium, it's whatever way it's written. So that means that in this case, heat is on this side. So what happens then if I put the equilibrium mixture in an ice bath? What does that mean? If I put an ice bath, which way is the temperature changing? Is it getting bigger, higher or lower? In an ice bath? Low, right? So essentially, I am removing heat. In other words, Le Chatelier, heat is being removed. That means that that side where it's at is getting lighter. So I need to compensate by going in that direction, right? So that means that system, put this up again. Actually, let me shrink this again one more time. System shifts to products, but that means that the value of the equilibrium constant is going to have to what? Increase or decrease? If I go to products,
increase.
Increase. Very good. Remember that in the cases where we change concentration, all that happens is the system reestablishes the same equilibrium. Pressure, volume, all that kind of changes. However, if you change the temperature, you not only shift the equilibrium, but you are now in a different equilibrium constant situation. Okay, don't forget that. you know what? You can always, let me see, I can share screen here. You can always go to your, where's the handout that I gave before? Okay, remember that you're always gonna be able to come here to this handout, and there's that table there at the top that tells you all of these changes, not all of them specific, but remember that it tells you know which ones affect the equilibrium constant, which ones affect just the equilibrium. All right, so you can always go. All right, see. Somebody had a comment on the chat. Oh, you guys were answering the question, right? Okay. All right, last one. I'm running out of space here on the bottom, so let me go over here. It's going to be the answer to number 3. Sorry, I ran out of space. What is the effect of decreasing the volume of the container? Now, this will only be meaningful if decreasing the volume of the container means that you're compressing gases, right? So in other words, delta V is negative. So if you decrease the volume, what happens to the pressure? Increases, right? Because remember that what you have is, it's called Boyle's Law. You learned it in Chem 1A. Pressure and volume go in, reciprocal relationships. So if I compress something, or as I decrease the volume, I'm increasing the pressure because there's less room in there. So the molecules of gas are bouncing more frequently against the wall, so that increases the pressure. Now, remember, again, going back to that table that I just showed you a little bit ago, right? The study guide. Where is it? Oops, sorry, that's not it. That's not what I wanted to share. It's the handout. So remember that pressure and volume will shift equilibrium, like it says here, dependent on the relative moles of gaseous, reactants, and products. Right? Only in that case are you going to see a change. I'm getting this thing from earlier, right? Only if you have a relative change, a change in the relative number of moles. So we had to look at this equation they gave us and see, is there a change in the number of moles, right? So we have, for reactants, we have 2 moles. For products, we have 2 plus 1 is 3 moles. So, okay, so who remembers which way the equilibrium goes when you increase the pressure? Which side is going to feel the pressure change more? Feel more of it.
That's gonna shift to less moles.
Right. So the side that has more moles is going to feel it more. Another way of looking at it is if you decrease the volume, that means that the concentration is increasing. But because you have more moles in here, the concentration increases more on this side than on this one. So you are going to shift, therefore, to reactants. So the side that has the more moles feels it more, right? So it's kind of like, oh, that side's kind of heavy, right? The right side's kind of heavy. So I've got to shift back towards the reactants, okay? So that's a pretty cool exercise I have in there for you. I think that one is in the PowerPoint. I don't think I put the actual answers in the PowerPoint. So hopefully you got a hold of this one. And again, you'll have this video available to you later on, all right? Okay, let me come back here, come back to the gallery. Let me pin myself again. Okay, there we are. Okay, any questions about Le Chatelier or equilibrium stuff? I'm gonna take a little break. I need to get something to drink, and then I'll come back and we'll do the rest. No, that problem is probably not on the PowerPoint. I just made that one up. So you are fortunate because you got to be here and you got to see it. And by the weekend, you'll have the recording of this and you'll get to see it there. Sorry. I'm treating you special. Okay, guys, let me take a short break and we'll be back in about 5 minutes. I need to get some, maybe like 3 minutes, like a 2-minute break. Okay, I'll see you in a bit. Okay, we are back. I forgot to pause the recording, sorry. I'll edit it later on, I'll do a post edit. Okay, so any lingering questions? I mean, like I said, you had to go back and review and do some more practice problems, but you understand what I'm saying about the 3 big things. One of them is understanding, what kind of information the equilibrium constant gives you. Secondly, what kinds of problems are going to require you to build an ice table. Thirdly, how to apply the Le Chatelier principle to different types of scenarios. So make sure you go back and you review those things and practice a few more things, okay? All right, let me go ahead and jump over here back to the our presentation that we had before. And let's talk about the next topic, which is actually acids and bases, your favorite and mine. All right, so one of the things that I've noticed is that we still have a bit of a problem identifying, if you're giving a chemical equation, who is the acid and who is the base. And what does the acid do and what does the base do? Identifying which reactant product pair actually makes a acid-base conjugate pair. Also remember, you have to memorize. I think I gave you a list of 7 strong acids that you have to memorize. Hint, that's one thing that you might want to put on your cheat sheet, the 7 strong acids. Because the idea is, I'm not going to tell you in a question in an exam whether an whether an acid is strong or not. You'll have to be able to identify. Okay. Again, calculate pH calculations given hydrogen or hydroxide concentrations. If you have a strong acid or base solution, what's the pH? So all of those are things that you should be able to do, right? Again, here's some of the skills that we need to have. First of all, what is the ionization equation for a weak acid or a base in water? Very important. Remember that I think sometimes we still struggle with that. I'll have a few things here I'm going to show you in a moment. Again, what's the equation for the reaction of a weak acid with a strong base or a weak base with a strong acid? We experiment with those when we do titrations, remember? And by the way, don't forget that your buffers and your KA, the double lab, both of those reports are due tonight via Canvas. So make sure you upload those. Don't forget. This is a strong due date, not a soft one. So please make sure you got those done. How to tell if an acid or base is strong or weak, and then how to use different kinds of information. You know what? Let's do that right now. Let's switch over here. Let's step out of here. Again, I'm going to bring us back here. I am going to pin this down and let's ask the question. What are some of the indicators or indications? Let me change this. It's easier to put it in. How do we tell if an acid is a weak acid? All right, let's practice with that. Who can tell me one thing that will tell you that an acid is weak?
It's not a strong.
Okay, you're saying it's not one of the 7? Okay, that's funny, but it doesn't work because I gave you 7. There's more of them, right? There are many more strong acids. You'll learn about them if you take organic chemistry. There's several acids that are pretty strong and they're not in the 7. So that one's not going to work. Just because it's not on the list, it won't be. Plus, remember that I told you just a few moments ago, I do have a bad habit of sometimes inventing things, inventing compounds and formulas. So, in the words of George Lopez, watch out. Now, how do you tell an acid is weak?
It only ionizes partially.
All right, so partial ionization, very good. That's one of them. It has a low percentage of ionization. Very good. What's another one? What if you look at the equation for the ionization? What do you notice in there? What's missing in here?
Reversible.
Very good. Double arrow. In other words, the ionization is reversible. So there's 2 ways to tell that ionization is partial. One, they give you the equation, you see the double arrow. Another one, they give you the percent ionization, you can tell it's very, very little. Okay, any other ones? There's several. I think there's at least 5 criteria we can use, we can apply. What's another one? What about titration? What happens if you titrate a weak acid, let's say with strong base? What happens to the equivalence point? Sorry. My hand is getting in the way of my writing. What happens to the equivalence point of a weak acid when you titrate with a strong base?
It becomes more basic.
Okay, so it's greater than 7, which for a strong acid, the pH should be neutral at the equivalence. Right? All right, give me another one. How about the pH of the solution? I'm gonna write down here. Let's say this is the molarity of that guy. When you have a strong acid, how do you calculate the pH of that solution? All right, so we take minus the log of the molarity of the acid. Because remember, for a strong acid, all of the acid is present in its ionized form. And therefore, the molarity of the acid is the molarity of hydrogen ions, and you can do that. But in this case, the pH is not going to be minus the log of the molarity. Why? Because of partial ionization, right? Cool. All right. Can you think of anything else? No? Okay, how about if electrolyte, very good, I like that one. That's a good one. So a weak acid, if we had a way of testing, and I think I did a little, I think in my demo of the acids and bases, I gave you a little test with the little white bulb and stuff. I don't know if that made it in the video. But a weak acid what kind of electrolyte would it be? Same, right? Weak electrolyte. So there you go. That's 5 of them. There's more. There's other ones we can think of, but I'll leave it at that. If you download the PowerPoint, I think I don't know how many I put in there, but there's definitely a couple more you could do. But I would say that those are the 5 more novel. The titration, for example, remember the titration curve. Not only does it have an equivalence point that's basic, but it also, remember, it has a little bump when you start, before it starts taking the, a little bump there. That's another feature, but I would say that's probably not as meaningful, because what we're really interested in with titration is to find the equivalence point, right? Okay, so that was a good little exercise there. So let's go ahead and come back here to our thing here. Okay, let's go back to the PowerPoint. Let me tell you a few other things that I want us to be on top of in terms of skills here. Here we go. Okay. Okay, so again, here comes our friend ice again, right? So you have to be able to apply everything we learn in the equilibrium unit to equilibria that involve, weak acids and weak bases. So ice tables. The difference here is that in most of these cases, there's another variable. So besides the actual molarity and the value of Ka or Kb, there's also the pH that is given. And sometimes that one is used, excuse me, to calculate, things in there. So it's like I told you, there's always like, there's 4 variables and they give you 3 out of the 4. And then you have to figure out which is the one that they're giving me, which is the one that I need to find out. Well, those are the kinds of things that we have here. Don't forget that there's also salt solutions that we have to work with, and whether salt solutions be neutral, acidic, or basic. I used to include this in the quiz, but because of timing issues, I can't do it anymore. However, let me show you something else. And I'm not gonna have time to do this, but let me show you you go back to our Canvas page. Back to our, okay, this is gonna take a little while because my computer, like I said, is a little slow, and not the connection, but it actually painting the screen. So here comes the modules. And and taking a little while. See, when I was doing this class online, what I did was I brought my office computer to my house, and that one has a lot of memory and a really good processor. It does things very quickly, so I could do it from there. And for 2 years, I labored using my iPhone as the camera and the computer for all the screen sharing. And it wasn't until I returned 2 years later to the campus that I was transporting my computer, and because I accidentally grabbed the top part of it, realized that there was a camera in there after all, but it was hidden. So for 2 years, I worked that computer without knowing it actually had a built-in camera. I just didn't know. Anyway, let me show you something. So I put in, this was in here last week, but I put it again this week for week 10. It's a page called Acids, Salts, and Buffers, a review session. I want you to go back and review that. So what it is was, I know that students struggle with these topics, all the time. And so what I did was I did a session. This was back in 2020, but this was in the fall semester, not the spring of that year. And I went through a kind of like a review about acids and salts and buffers. And in here are the notes. So what you can do is I want you to go back and review that. In that video and in those notes, I go through basically all the things that I just told you about. Okay, how do I tell something's an acid, something's a base? How do I tell conjugates? How do I tell something's a weak acid? How do I tell, how salts work, especially if they are, conjugates. So remember that the idea is that actually, let me put a problem here. I had a little extra problem here for you guys, and this is not in your PowerPoint, but I'm going to put it anyway. Here. Actually, there's two of them here. Let's do these. Let's do this one first. Like I said, this is not. Let me come back out of the sharing. So again, please go to that page that I put in there on Canvas, and please review it as part of your studying, and you'll be able to, get an idea to review that slide that I show you about all the different things about acids, bases, KAs, all that kind of stuff. Let me go back here and let me give you a little practice problem here. Okay, here we go. Oh. I hope you guys can see it. So it says here, given there's three substances here, HF, hydrofluoric acid. And by the way, you notice that when we go through these things, there's a section there that I haven't really practiced a lot, which has to do with acid strength. Make sure you read through that and are aware of it. That may be something you want to put on your cheat sheet, how to tell if I give you two different acids, and I only gave you two trends in there. One of them is for the oxy acids, and one of them is for the halic acids, HF, HCl, HBr, those kind of guys. But anyway, HF, and there's the Ka for it, ammonia, and there's the Kb, and then hydrocyanic, HCN, and it's Ka. Now, you see those three values there, but here's the question. Classify the salt solutions as acidic, neutral, or basic. I know. People just get all bent out of shape with these kinds of questions. And a lot of it has to do because we forget how to operate with ionic compounds, right? How to operate with ionic compounds, how to identify who is who in this compound. A salt is essentially an ionic compound, right? Which means it has a cation and it has an anion. The anion and the cation, either one can be either mono or polyatomic. So let me give you a hint. So this is sodium cyanide. So what I'm going to do is I'm going to put this guy in water. What happens when I put that guy in water? It dissociates into sodium. And remember, once you identify the metal, everything else is the anion. This is not C ions and N ions. No, no, no. It's CN. And based on this being a +1, this is -1. Now, what's the strategy here for this kind of problem? Strategy is are either the cation or anion a conjugate of a weak, respectively, base or acid. Let me zoom in a little if you can see that better. So that's a strategy. Are either the cation or anion a conjugate of a weak base or acid? Now, I didn't go through the trouble of giving you these values up here of these Kas for no reason whatsoever, right? So when you look at these two here, does sodium look like it would be the conjugate of a strong acid or base? No, right? Because anything you pair up with sodium is going to completely dissociate. Look, it just did right now. But what about this guy here? What does that look like? That looks like the conjugate base of this guy here, HCN, right? So that means that this guy is going to, oops, sorry, it's going to react with water and it's going to produce HCN plus OH minus. So the idea here is, remember the strategy. I had to figure out, okay, who are the ions? And is either one of them the possible conjugate? And this is where, again, you have to develop that skill of looking at a formula and saying, hey, that guy plus a hydrogen makes a weak acid. That guy minus a hydrogen makes, I'm sorry, that guy plus a hydrogen makes a weak acid. That guy minus a hydrogen makes a weak base, right? In other words, you have to be able to identify these things. And this is where that skill of pairing conjugates comes in. So this guy is the conjugate of HCN. HCN is a weak acid. That means that the cyanide ion is a weak base. And therefore, when you put it in water, this guy is not going to stay like that. It's going to create some hydrolysis, right? We call this base hydrolysis. And what's going to happen is that our OH minus is going to make this solution what? Basic, right? It's going to be a basic solution. Okay, I'm going to let you guys do the next one. How about you do this one? I'll tell you what the ions are, right? Again, the ions here are NH4, which is the ammonium ion. And here is chloride. You could think of chloride as the conjugate of HCl, but HCl is a strong acid, which means that chloride is not going to be a strong base or even a weak base at all. So what am I looking for here? I'm going to let you work it out and tell you that this particular salt is going to be slightly acidic. Anybody tell me why? Why does the ammonium ion give me a very good? It donates a proton. And H4 is the conjugate of this base. So as a conjugate, it's a conjugate acid, and it donates a proton to water, gives me back NH3, and then I get H3O+. There you go. Again, let me repeat it. This is where it is so crucial that we review and master that whole scenario, that whole set of things about, who is an acid, who is a base, what makes a conjugate pair, and what does each one do. Now, the next one is going to give us a combo. So it gives me both this guy and that guy. Now, if you guys are struggling with this, let me show you. You have this in your handout, actually. Let's go back to our handout that you're going to get in the exam. And you can see here on this table that I copied here, and this is from the old, I think this is the 5th edition of Pro. It tells you what type of salt. Cation from a strong base, anion from strong acid, cations from strong base, anion from weak acid, cation from weak base. It gives you all the scenarios and even has some of the examples here that I just gave you, right? And it even gives you here what happens if the cation is from a weak base and the anion from a weak acid. So it says here that you want to do is you want to compare the relative values of Kb and Ka. So I'm gonna let you guys figure that one out. You can go back home and look at that and say, okay, so if this is the conjugate of that guy, and this is the conjugate of that guy, ammonia is a stronger base than HCN is an acid. So that means that the ammonium ion should be a lesser acid than the cyanide ion is a base. And so this guy is going to dominate, right? So this should give me, oops, sorry. I forgot that I was sharing. Sorry, let me go back. Go back to our main screen again. If this is the conjugate of ammonia, and this is the conjugate of HCN, ammonia has a Kb that is larger than the Ka of HCN. That means ammonia is a stronger base than HCN is an acid. Therefore, the conjugate should be a weaker acid than this conjugate is as a base. Therefore, CN hydrolysis dominates. So you have this guy going on, you have that guy going on, but this guy is going to go at a greater rate than this one. So you will have, therefore, sorry about that, you're going to have a basic solution. So I need you guys to go back and review that. Notice that I did give you the table. You can have it in the in your handout. You don't have to copy this, but you need to understand how this works. Okay. Okay. So, what would you say would be your struggles with this kind of problem? What do you think? Assuming you get past this, I mean, I'm hoping that you can get past the dissociation of the ions, right? So would you say your main struggle is identifying, you know, what these guys are doing here? Probably. Is that an accurate thing? Yes, Dylan, I am going to be posting the recording. Unfortunately, I probably won't have it until the weekend. Okay, you're confused on that part I just pointed out. The last one you mean? Salt, when the two of them are conjugates. Right, so again, if you go back to that, once you get an understanding, you can see again our handout, right? Our handout, and you can see it here in this table here, right? It's going to be table over here. Oh, yeah, it won't work for me now. So, sorry. It's repeat. Oh, here we go. This table. So you can see that, just look at the different scenarios and it tells you what's going to be the pH. So for example, we just did ammonium chloride. You saw where it was acidic and we showed you why. So what I need you to understand is why. So when you have both the cation and the anion be from conjugates of a weak base and acid respectively, what you have to do is that you have to compare the bases Kb with the acids Ka. So right now, what we found was that for the example I gave you, you had the Kb of ammonia was bigger than the Ka of HCN. And the result is, as you can see here, is you got a, sorry, that's too big. You can see that in that case, what we got was that the pH was basic. In other words, it's a basic solution. And what I did was I explained to you why. And the reason was, since Kb of ammonia, right? What we said is Kb of ammonia is larger than the Ka of HCN. In other words, what that means is that ammonia is a stronger base than HCN is an acid. Now you look at their conjugates. The ones that are going to be in the salt are going to be their conjugates. Remember, the stronger something is, the weaker its conjugate is. So if this is a stronger base, that means that its conjugate is going to be a weaker acid than the CN is. If you want, I mean, you can do the math. You can go back and look at these Kas and Kbs and calculate the reciprocal, right? We had the formula, remember, Kw equals Ka times Kb. So if you have the Kb, you can calculate Ka. So you can do that and show and prove mathematically that this statement is correct, that ammonium is a weaker acid than cyanide is a base. So when you combine these two, right, in a salt solution, the one that's dominating will be the one that is a little stronger, which is the basic one. And so that means it's going to create a basic solution. All right. So please go back and review that stuff. Again, like I said, I know it's a little tough. I have another problem here for you guys to practice. And let's go to it. So, up here. Shrink a little bit. Saccharin, did you know that saccharin is actually a monoprotic acid? Did you guys know that? I bet you guys didn't know. The pH of a 4.45 times 10 to the minus 3 solution of this acid is 2.53. What is the Ka of saccharin? There you go. So this goes back to our presentation here. Go back for a moment here to our PowerPoint. And one of the things that I mentioned here was vibrations. I guess I don't have it in. Well, I guess I don't have it here, but I had I used to have a slide here where it showed, you know, what are some of the methods for finding the value of Ka. Now, in your lab activity, you did 4 of them, right? Now, the one that I typically test students on is the one where you make a solution of a known concentration and you find out what the pH is, right? So this sounds like, that's right. There you go, that's right. Saccharin, well, I don't know what saccharin is. So it says it's an acid. So let's just call it HX. And let's say that it is in equilibrium with, you know, the typical ions. Again, I don't know what saccharin is. I don't have to know what its formula is other than to find out how to make this kind of a solution. But let's say somebody made it for me. One of the people, my good coworkers in the lab, made it for us and told us that's the molarity of it. So this is initial, this is the change, this is the end, and this is 4.45 times 10 to the minus 3. We already have it in molar units, so we don't have to worry about that, right? Now, again, like I said, because we use that X for the scientific notation, as opposed to the way, you know, a lot of engineering students will, which is this way, which is somewhat convenient because it avoids using the X. But because most of us will use the X, I will use here a different letter. I'm going to use Y. And then I'm going to make some of that. And so I have 4.45 times 10 to the minus 3 minus Y. This is Y. This is Y. Now, remember, the question here is to find what is Ka. So Ka is And tell you what, I always suggest that you write out the expression just so you keep track of things properly. I know some of you want to shortcut your way to writing out the final thing, but my experience is that students many times get lost doing that. And so this is going to be y squared over 4.45 times 10 to the minus y. Okay, now here you go. You're going to say, should I use an approximation? Hold on. The question right here is not finding y. The question is finding Ka. So this is where you have to identify who your unknown is. This is your unknown. Y, again, if we were doing Professor Rollback's system, putting a second E, you can get what Y is because Y is the concentration of hydrogen ions, right? Right here. And they gave us the pH. So that's 10 to the minus the pH, which is 10 to the minus 2.53. Okay, this is where you're gonna have to go to your calculator and figure out how your calculator does that kind of a problem. Okay, I'm gonna leave it at that because this basically gives me what this is, what Y is, and I can fit it in there. Once I fit it in there, I'll decide if this is gonna be significant or not. But basically, I'll just have to plug in. And the rest of the problem becomes math. So remember that this is perhaps the more common way of finding the Ka of a weak acid is make a solution of a known molarity, measure the pH of that solution. You probably have to do several measurements, right? And then you can do this. Remember that in your lab report, you're going to have a few other ones. You're going to have the pH of the solution of the conjugate base. But again, in this case, I don't know that you can get a conjugate base of saccharin as a salt. I don't know. I'm just throwing things out here. You can also do a solution that is equimolar between the two, the conjugate and the acid. And then we also have using the titration curve, which doubles up as we saw in that exercise that you guys just did. You can use the titration curve to find the value of Ka. So, but for our purposes, if I were to put upon an exam, it would be more like this type. I would give you a solution of the substance, and then we would find what is the Ka, or I might put a base and ask you to find the Kb. So again, just be aware of those possibilities. Okay. Let's do one more practice problem here, and then I'll stop for any last minute questions. I did not get a chance to cover solubility, but I do in the video that you can access. Okay, but let's look at this one here. So, shrink this just. Oh, there we go. So here are three, and just so you're aware of this symbol here. This is a way that we write acetic acid. We sometimes write as HOAC or sometimes simply HAC, just an abbreviation. I just didn't want to have to write the whole formula in there, but technically what it is, it's, H, it's CH3COOH. Sometimes they write it as HCH4CO2. I mean, there's all kinds of different ways of writing it. When we study organic chemistry a little bit, we'll see the advantage of using this format here because it identifies a family of compounds called the carboxylic acids. Anyway, so here's the Ka for this one, and here's, look at this. This one has a double Ka, Ka1, Ka2. Okay. Which of the following solutions has the highest pH? In other words, which one is the most basic? So this one is an interplay between understanding what kind of information the equilibrium constant gives you, and then what does the Ka of an acid tell you about the corresponding conjugate base? Okay, so can you think of a strategy here? What would you do? This is essentially a multiple choice question. So I don't know you guys, but one of the essential strategies of multiple choice is eliminate the obviously wrong ones first. Right? If I'm looking for the highest pH, what would I not have in here? What kind of substance would not be in there? What would not have a high pH? Just unmute yourself and tell me. What substances don't have high pH? Have low pH?
Acid.
Very good. So, strategy. Number one, eliminate the acids. Right? So which ones are acids here in these five?
A and D.
A is an acid, right? It's the same one you see up here, right? Who else? It's right here. Okay, so based on this first point here, we eliminate it. So now we're down to three options. And all three of them, as you can see, are salts. So that means that we are identifying conjugates. That guy there, that guy there, and this guy here. So those three anions are going to be conjugates, right? Now, remember what we talked about earlier. These are conjugates of weak acids. Therefore, they are going to be acting as bases. The question is, which of them is the strongest base? Which of them is the strongest base? Well, what have we said about conjugates? If I'm the strongest base, I am the conjugate of which acid? The what acid?
Weakest.
That's right. The conjugate of the weakest acid. Okay, let's go back at the list here. Which of these three is the weakest acid? Which of those three is the weakest acid?
AA2.
Very good. This guy here, I'm going to put this point number 4. That's the weakest acid because it has the lowest value of AA. Now comes the question. What does that ionization represent? Ka2. Well, we look at the formula of the initial acid H2CO3, and it has 2 ionization constant. That means that it must go through 2 steps. Remember that we said that polyprotic acids ionize in steps. They don't do it all in one shot. They do it in steps. So this is the second step, right? This is the step or the second ionization is the one where you had landed at 1 hydrogen. And now you're going to do H plus CO minus. So this is the conjugate of the weakest acid. Okay, so which of these salts, B, C, or E, have that ion as their anion? That one, excuse me, that. C, right? Sodium carbonate. So that salt is made with this guy. That guy is the conjugate of the weakest acid. Therefore, it is the strongest base, and therefore it's going to generate the most basic or highest pH. Again, my recommendation, go back, is, always, you gotta start from that skill that I told you about, recognizing, identifying, first of all, what does the acid do in an equilibrium? What does the base do? How do I identify, who is a conjugate with whom? And how do I play with these values of Kas in terms of applying them to the relative strengths of these things? I think right now, because I don't think you guys have started studying that hard, and all you're probably working off of, what you've done in homework and stuff, and the work you did this week. It's okay. Don't worry about it. I'm not gonna review buffers because you guys had the quiz last week, but you've done all this whole lab work on it. So hopefully that helps. Let me finish here with our presentation, and I'll let you go off. And maybe what I'll do is, here we are. So again, titrations. Oops, sorry. Okay, buffers, the Henderson-Hasselbalch equation. I'm gonna give you that equation in your handout. So the important thing is not so much memorizing it, but knowing how to use it, right? What are the components, the ingredients, the recipe for a buffer solution? You have to have a weak acid and its conjugate. They have to be in relatively high concentration so they can absorb incoming protons or hydroxide ions. And it's very important to remember that a desirable buffer would have a pK near the desired pH. Near the desired pH. So you want to have essentially a situation where the base and acid concentrations are fairly close to each other, but the pK is very close to the pH, so that changes in these concentration ratios are not going to make a huge dent in the pH, right? Again, if you guys want to go back to the quiz that we did last week, some of the practice problems, and then this is the slide I was looking for, the 4 ways of obtaining the Ka. This is all, again, this was crossed out, but that's the one you guys did in your lab. Okay, we have not had much of a chance to practice on this, but we have a quiz this Thursday on KSP. So please go back and review the whole idea of solubility. We have alluded to it, and we did a lab this past week where we calculated the KSP of a substance. Remember the potassium hydrogen tartrate, which is actually cream of tartar. And so hopefully that exercise will carry you through some of these calculations. Tell you what I'm going to do is, if you want later on, I can put in, I don't know if in the video that I posted in, again, there's several things here. This is a typical problem that we have in solubility is if you're given the KSP, find the concentration of one of the ions, or let's say the concentration of dissolved substance. In other words, the saturation concentration of a substance. And if you are given conditions of, where one of the ions is involved, it's a hydroxide, which means it's involved in pH calculations. How does that affect it? So I think that perhaps in the video, I'm sorry, I don't know if in the video that I posted, let me come back here tomorrow. I don't know if in the video that I posted in the Canvas page, if it includes the solution of these problems. So I'm gonna check it. And if it's not in there by the weekend, I'll put a second video where I walk you through the solution of those solubility problems. And maybe I'll put in another one. I really haven't hit this that much because we really we just haven't had a quiz on the topic. And in the labs, we've exploited differences in solubilities, but we haven't really gone deep into quantitative stuff because when Dr. Perot built the lab manual, she kind of took out a lot of that stuff. So it wouldn't blur the experience, which really is just the strategies of separating ions and stuff like that. And the mathematics behind it are really a little bit kind of like beyond our interest right now. But go ahead and make sure you study that. You know, this week, technically, we didn't have any reading assignment, any contents posted. So we're trying, I gave you this week, last week and this week, basically to catch up with all of this acid base and buffers and solubility stuff. So hopefully by Thursday, you have completed all those studies. So because you have a quiz on Thursday about solubility. And we're going to be studying the group 3 and 4 ions. So we'll revisit this whole issue of solubility. And once more, we'll address the whole thing of how to use the acidity of the medium to change the response of solubility of different things. So so here's the plan. We're gonna cut it here unless you have any last minute questions. I will post this recording by the weekend, I hope, on your Canvas page. You can stick to the PowerPoint that's in the Canvas page already, and you can watch that video to complete the stuff that maybe I didn't cover, because most of the problems that I solved here were new ones. So what I'll do is I'll post this video with those problems in here. I'll give you the blank sheets, and then you can go ahead and, because right now, what I'm looking at that I wrote in here, it doesn't make any sense. So you really have to follow through. So what I'll give you is a video, and then I'll post the blank practice problems so you can do them by yourselves. Okay, do them again. All right, any other questions topic wise or itinerary wise? Anything else?
Dr. DA,
Yep.
the PowerPoint that you were showing us with all the concepts, are you gonna post that one too?
That one's already there.
Oh,
I
okay.
just rearranged the slides in my version, but it's all in there in the Canvas page.
Thank you.
Just remember that you'll need to download the file, not just see the slideshow. You need to download the file so you can see the answers, right? I don't know if I can. Let me see if I can make that work. Hold on a second. Let's take, for example, let's take, for example, I'm gonna share the screen just for a moment so you can see what I mean. So if you download the file and you enable the view notes, and again, it depends on whether you're using a Mac or using a PC. But you can see here, this is not the slideshow, but the file, and I have it in 3 frames. And you can see, for example, the question: how do we tell if an acid is a weak acid? On the bottom frame here, these are the answers down here, right? You can see them there. But you'll have to basically be able to open the file in order to see that. And again, like I said, if you have a Mac and you're using the Apple equivalent, Mac equivalent of PowerPoint, you may have to enable something in there. So I just know that students have had a hard time sometimes, but they can figure it out. All right. Okay, guys, I know it's been a long time here tonight, but thanks for showing up, and I hope that I don't know that this helped in terms of understanding, but I think at least it'll help in terms of you knowing, okay, I got my work cut out for me. This is what I need to I need to do better with this. I need to understand this other thing better. And I think you can go back and study. Remember, the exam is on Tuesday, so you only have a few more days, and we might think, well, that's plenty. You know, things get in the way. So I would recommend, you know, try to catch up and make sure that you're solid. Next week, lecture-wise, we start a new unit on thermochemistry. We're gonna start with a little review of your Chem 1A stuff, and then we're gonna go into introducing other concepts in thermodynamics, like for example, entropy, from a quantitative point of view, and the second law of thermodynamics. So it'll be, again, it'll be pretty heavy, but that's okay. Just make sure that you cover all this stuff in time for Tuesday's exam. And again, it'll be the same. We start at 5:30. We'll be there in the room. It'll be, I haven't made it yet, so just imagine maybe 10 questions, 10 points each, and something like that. And you'll have to show your work and your calculation. You'll answer on a separate piece of paper. Some of them will be calculations. Some of them might involve just explaining things. So just make sure that, you know, the questions that I've given you here on the practice, both the ones in the PowerPoint and the ones we did today, have a good combination of all of those. Thanks a lot, guys. Have a great evening. And if there are any lingering questions, just put me a message in Canvas and I'll get to them by tomorrow morning, okay? I start my interviews tomorrow at 8 in the morning, so if I can get them before that, I'll do it, but if not, I'll do it afterwards, okay? So by no later than noon, I will answer any questions you post on Canvas for me, all right? Take care, guys. Have a great evening. I'll see you on Thursday.